Hello students, it's Mr. Zafiro here, and we're going to try to get up and running at a distance. These are Isaac's notes from last year. I thought I would use them. We did a good job and it would expedite us getting through our lessons. Now, these notes are actually available to you in the regular announcements that I make every day. If you take a look here, here are the notes that we're going to be using right now. 3U dynamics in PDF format. Here were the previous notes, but we're starting right here. So all the notes that we're going to be using, they are available online. I'm going to be adding to them during these videos, but they are available there. So what we're doing right now is we're moving into chapter 3. And today I hope to cover section 3.1 and section 3.2. I'll put questions for homework up that you can try, and as you know, I also put the answers up. I put a discussion thread in there if you do have other questions and you want to ask me them. And there's also a video available on today's announcement on how to use the discussion thread, and you can look at that as well. So here we go. We want to start talking about the force of gravity. We talked about it briefly when I gave you sort of a list of all the common forces we'd be dealing with. And we're going to start with the force of gravity near Earth's surface. Now, gravity is a very interesting force, and the reason it's a very interesting force is gravity is a force that is caused by mass, and it acts on mass. It's an interaction between masses. This is the way that Newton envisioned it. There's an old story about him sitting under an apple tree and an apple falling on his head. And who knows if it's true or not, but that's the lore. And it started him thinking about all things gravitational. And one of the things he started thinking about is that any object that has a mass, so as soon as it has a mass around it, he envisioned something called a gravitational force field. It's a force field or just a field, and it's associated with it. So what we have right here is a picture of that, the Earth. And around the Earth is this invisible field called the gravitational field, and it's caused by the mass of the Earth, and it has an effect on all other masses near its surface. So for example, if you had an object here near the surface of the Earth, it would feel a gravitational force towards the Earth. And the Earth's gravitational field has a certain magnitude to it and a direction, because the symbol for gravitational field is G with an arrow over it. It's very similar and associated with the acceleration due to gravity. It's the same number, but the value in terms of unit has been changed. So what it's saying is this. If you have an object near the surface of the Earth, it has the Earth's gravitational field having a force on it. And for every 1 kilogram of mass that an object has near the surface of the Earth, it will feel 9.8 newtons worth of force in a direction which is negative because it's down towards the center of the Earth, and towards the center of the Earth is all down force. So as it says here, for every 1 kilogram of mass that an object has, there is negative 9.8 newtons worth of force. This is known as the gravitational field. Now, field is an idea that scientists like to use when the influence of an object extends beyond its physical limits. So even though the Earth ends here, its influence is a way out here. We call that a field. For example, at our school on the second floor, during lunch. No teacher is there to enforce the rule that no one can be up there during lunch on the second floor, but the influence of the teachers and of the administration extends up there. Its effect is there even though they're not there. Well, even though the Earth ends right here, its influence continues beyond it. That's why we have a moon that's going around the Earth and various satellites. When you have influence or action at a distance, what scientists like to call that is a field. And it's measured in newtons per kilogram when it's a gravitational field, because so many kilograms of mass will feel a certain amount of force. Now, if we break down newtons into kilogram times meters per second squared, because that's what we can break a newton down into. Remember, F net equals ma tells us that a newton is equal to a kilogram times a meters per second squared. What we then can do is cancel out the kilograms and we're left with meters per second squared. So newtons per kilogram and meters per second squared are equivalent. Meters per second squared is usually the unit that we use when we're talking about acceleration due to gravity near the surface of the Earth, negative 9.8 meters per second squared. When we're trying to talk about the influence of Earth's gravity on objects near its surface, we don't use the meters per second squared, we use newtons per kilogram. But what I've proved to you here is that newtons per kilogram and meters per second squared are equivalent. All right, well, let's continue with the node here. Remember, there's no real need to go crazy and copy this down as I'm talking. The node is available online for you to download or do what you want with it. Now, this force of gravity, especially near the surface of the Earth, it goes by another name. It goes by the name weight, which is a very common term that you've heard before. So in terms of an equation, we're saying weight, a vector, it has a magnitude and a direction, is equal to the force of gravity. A vector has a magnitude and a direction, and it is equal to the mass of the object times the gravitational field strength near the surface of the Earth. Look how detailed I'm being about when I'm talking about this. The force of gravity, right? This is the force of gravity. This is the force, is equal to the mass of the object times the gravitational field strength. This is the field. Don't confuse these two. This is always the same thing. The gravitational field strength near the surface of the Earth is negative 9.8 newtons per kilogram. So if I want to calculate my weight, my force of gravity when I'm on the surface of the Earth, what I do is I take my mass in kilograms, which is 76 kilograms, and I multiply it by the gravitational field strength near the surface of the Earth. Once again, I'm being very deliberate about how I'm saying this. I multiply them together, and I get 76 kilograms times negative 9.8 newtons per kilogram, and there's my answer in newtons. The reason it is in newtons is the kilograms cancel out. All right, and my weight, my force of gravity due to the Earth's gravitational field strength is negative 749 newtons. It is a vector. It has a direction. But this is the equation that we use to calculate it all the time. So I strongly suggest you put that equation into your equation sheet. Now, the next thing we want to talk about is the law of universal gravity, the law of universal gravity. And it applies to any two objects in the universe. It mostly applies to large celestial objects. For example, the force of gravity between the sun and the earth, the force of gravity between the earth and the moon, things like that. The force of gravity between the sun and Jupiter, the force of gravity between Mars and its two moons. And it's a completely different symbol It's F big G. What's up, big G? All right. And it has a different formula. So force of universal gravity, different, is equal to this big G, which I'm going to get to in a moment, the mass of the object to one of the objects involved, the mass of the other object involved, and how far they are apart squared in the denominator. So what we have here is this universal gravitational constant. It's a number that's used to make sure that when you multiply the mass of the two objects involved in the attraction and you divide it by the distance between them squared, you get the right answer. So for example, let's say you have mass 1 here and mass 2 here. This could example be the Earth and the Moon, and you want to find out the force of gravity between them. Well, you'd have to know the distance between the Earth and the Moon. You'd have to know the mass of the Earth. You'd have to know the mass of the Moon. You would put this into the equation, the mass of the Earth, the mass of the Moon, divide it by how far apart they are squared. But in order to get the correct amount of force between them, you have to have in the numerator the universal gravitational constant, which is a constant value. It never changes. It's 6.67 times 10 to the negative 11 newtons times meter squared divided by kilogram squared. So back to our example. The Earth, the Moon, there's a force of gravity between them. They're attracting each other. Remember what Newton said. Gravity is a force that's caused by mass and has an effect on mass. The only reason the Moon stays in orbit is because of this gravitational attraction. So now we're going to use this equation here to find the force of gravity. Force of gravity, let me pick a different color there. Force of gravity between the Earth and the Moon. So the first thing you need to do is put in 6.67 times 10 to the negative 11 newtons meters squared all over kilogram squared. That is the first term in the numerator. Then we have to put in the mass of the Earth. Now the mass of the Earth is not something I have memorized. I just looked it up. 5.98 times 10 to the 24 kilograms. Then we're going to multiply it by the mass of the Moon, which is 7.35 times 10 to the 22 kilograms. That's all in the numerator. Then in the denominator, we're going to put in here the distance between the Earth and the Moon, center to center distance, and we're going to square it. And the distance between them, center to center, is 3.84 times 10 to the 8 meters squared. So you multiply everything in the numerator, then you press equal, then you divide it by the denominator squared, and we get 2.0 times 10 to the 20 newtons. Please try this in your calculator yourself. Please put it in and see if you get this answer. Notice that when you're trying to calculate the force of gravity between these two massive objects, any two massive objects really, we're going to get an answer in newtons, forces in newtons. If we're talking about masses, we're always talking about kilograms. If we're talking about the distance between them, we're talking about meters, not kilometers. And this is the force of gravity between them. Now, when you key in to your calculator, depending on the calculator you have, times 10 to whatever, okay, let's say Z times 10 to the Y. This part right here, make sure you use a button, depends on the calculator, that looks like EXP or EE to key it in. So I'm going to be posting some homework on the website. The textbook is available on the website. The answers to the homework is available on the website. If you have questions, you can ask me through the discussion thread. We'll get through this as best we can. None of this is going to be perfect. I'm learning as you're learning. I'll make a million mistakes a day, but together we'll get through it. Stay safe.